what will be recorded is our audio and whatever it is that shows up on my screen.
Okay.
Okay. Now, usually the best way to do this is to have the student bring the problems to the table. And for Algebra 2, that should be relatively easy for you to verbalize problems. More so than like geometry. If it was geometry, it would be difficult to verbalize problems. You would almost need to take a picture of them with your cell phone and send that to my email address, and then I would bring that up on my screen. But with Algebra 2, I'm guessing that you can probably verbalize those.
Yeah, that shouldn't be a problem.
So let's go ahead and give me your first problem. I'll write it on here, and then we'll solve it.
All right. So the first problem I wanted to do, it's got a table.
Okay.
And the x values are 0 through 5.
Okay.
And the y values are 2, 4, 0, -10, -26, and -48.
Okay.
And I have to find the quadratic equation in the form y equals ax squared plus bx plus c.
Okay. There's 3 variables we need to solve to come up with this equation. What are they?
A, B, and C.
Correct. In other words, our final equation is still going to have a y in it and still going to have the x's. So we need these 3 constants, A, B, and C. Well, we have enough data here so that I can come up with 3 equations and 3 unknowns and solve for A, B, and C. Okay? So what's C?
2.
Correct. So immediately we can replace that with 2. And that solves for 1 variable pretty easily. And when x is 1, what is y?
4.
So we have the equation 4 equals a times 1 squared plus b times 1, which means a plus b. Okay? When x is 2, what is y? Oh,
0.
So 0 equals a times 2 squared plus b times 2, which is equal to 4a plus 2b. Okay. Now we basically have 2 equations and 2 unknowns, and we can solve for a and b. Let's set it up more in standard form. A plus b equals 4 from this equation, and 4a plus 2b equals 0 from this equation. Now, I have a system of 2 equations with 2 variables. How do I solve that?
You could do substitution.
Could do substitution, but usually when you're looking at both equations in standard format, elimination is going to be.
Okay.
Okay. If one of the equations was of the form A equals 4 minus B, then substitution would be better, because I have one variable fully solved for. But when they both come in standard format, I'm just going to suggest that elimination is the way to go. How can I eliminate A? It's called equation 1 and then equation 2.
Well, you could multiply everything in equation 1 by 2.
Okay, that gives me 2A plus 2B equals 8.
And then subtract.
Okay.
Subtract equation 2.
Should I subtract? I can do 2 from 1 or 1 from 2. Which should I do?
1 from 2?
Yeah, especially since I've written it. At the very minimum, I'm going to get a positive exponent there. Okay? What's the right
side? Negative 8.
So A is negative 4. Once you get A, now you want to go back to your simplest equation, which is the original one. If A is minus 4, B has to be what?
8.
So there's your solution to the quadratic. You have y equals minus 4x squared, that's what A is, plus 8x plus 2. And if your life depended on this, you'd probably want to check it for a couple of other values. Right? In other words, I said to you, your life depends on this being the correct answer. Well, we derived it from these 3 values. So let's substitute x equals 3 and see if we get minus 10. Okay, so y equals minus 4 times 3 squared plus 8 times 3 plus 2. If this comes out to be minus 2, we probably have the right answer.
Okay.
Well, 3 squared is 9, times minus 4 is minus 36, plus 24, plus 2, minus 10. And that pretty much convinces me. If my life really did depend on it, then I would try 4 and I would also try 5. But if a test just depends on it, then I'm 99% confident we have it correct.
Okay.
And there's your answer.
Well, so what you have to do is you find C and then you just you get the system for A and B.
Basically, when you have 3 variables here, you have to solve them. You need 3 equations.
Okay.
Well, one of them is very easy. When I substitute 0 for x, well, C is y. So if y is 2, C is 2. So one of the variables is very easy to solve for. Once we solve for that one variable, then we only need to find 2 equations, and we'll only have 2 unknowns. So we can get an equation from that x, another equation from that x.
Okay.
In other words, you always need the same number of equations as you have variables. It just so happens that with a quadratic, C is very easy to solve for as long as you know what y is when x is 0.
Okay.
All right. What else?
The next one, we have the quantity of the quantity of the square root of 2 minus the square root of 3 divided by 3 minus the square root of 3.
Okay, we want to simplify this expression.
Yes.
Mathematics does not like irrational or imaginary denominators. Okay?
Right.
It doesn't really make any sense if you think about it. When you're doing division, you're splitting something up into a certain number of parts. Well, how can you split it up into an irrational number of parts? So, we don't like that as a denominator. We have to rationalize.
Okay.
How do I rationalize? First of all, let's take a simple problem like this. Same irrational denominator. How do I rationalize that?
Well, you'd multiply the numerator and the denominator by by the square root of 2.
Which produces the
right.
real denominator. This is a much better answer than this is. It's the same number. If you put that into your calculator, you'll get the same number as that. It's just that this is more mathematically palatable. Okay? Same thing for the problem you gave me. We want to make the denominator rational, not irrational. And the way you do that is by multiplying the denominator by the conjugate. That's always the conjugate.
Okay.
If we multiply the denominator by that, we have to multiply the numerator by that. Because remember, the overriding thing is I can only multiply fractions by the number 1. Can't multiply it by just anything I choose to. I can only multiply it by 1. What's the denominator end up in?
9 minus 3.
Yeah. In other words, it's useful to recognize that that's the difference of squares. And when you multiply them back together again, you can either FOIL them or recognize that that must be this squared minus that squared.
Okay.
And that's how you get 9 minus 3 or 6. Now, the numerator becomes what? Just go ahead and FOIL it.
3 root 2. Root 6.
Plus root 6.
Minus 3 root 3. Minus 3.
Okay. So how many roots? We've got nothing in common, huh? So we got 3 root 2 minus 3 root 3 plus root 6 minus 3. That's the numerator. That's the answer. Fully simplified.
Okay.
You can't really simplify it anymore.
Okay.
At least not that I can see. You could do some exotic algebra. Try to pull a root 3. No, that's not going to work. Yeah, you could change it. I don't know if it would be a simplification or not. But you can't combine those two. I could separate that into root 3 times root 2, but that doesn't really help anything. Still can't combine anything. Now, I could separate this into four fractions. That fraction, there's this fraction, there's this fraction, and there's this fraction. And that actually might make it look a little simpler, but I don't think it's worth the trouble. I'm guessing that this is going to be the answer.
Okay.
Okay. What else?
Let's see. This one we had to sketch a graph of the function f of x equals x cubed minus 2x squared minus x plus 2 by finding the zeros and determining the sign of the values of the function between zeros.
Okay.
Label the ordered pairs for the x and y intercepts.
Okay. First of all, quadratics can always be solved for the zeros. Even if you can't factor it, you can use the quadratic formula. All right?
Okay.
Cubics are not such. Cubics and quartics, third and fourth degree polynomials, are unbelievably difficult to solve. It's only been in the last 400 years that we know how to solve them. But a particular form of it is easy to solve. The kind they're giving you here. Because it lends itself to grouping. Okay, so here's how I'm going to solve this. Okay, I'm going to group those two terms, and I'm going to group those two terms. And the reason it works is because the ratio of the coefficients are the same. This is 1 to minus 2. This is 1 to minus 2. As long as that ratio of the coefficients of the x cubed and the x squared is the same as the coefficients of the x and the constant, then you can group it.
Okay.
Now, before I put parentheses around everything, make sure we don't change it. So this stays like that. But now if I want a minus sign, what does the right-hand side need to be? Remember, I cannot change the function. That's the key.
You need to have it need to be x plus 2?
Correct. Whoops, excuse me. It needs to be x minus 2.
Okay.
Notice that if it's x minus 2 and I remove the parentheses, I've got this. And that's the key. You put the sign of whatever you need to put, it doesn't change the function. In other words, once I've got it like this and I remove the parentheses, I've gone back to there. And that's the thing you should always be looking for.
Right.
You cannot change the function. If you've changed the function, you've made a mistake. Okay? Now, I can take this expression. What's the greatest common factor I can remove from it?
X squared.
What's left?
X minus 2.
Now we're going to do something that you're not used to doing. You're used to pulling out a greatest common factor, but usually it's a monomial term. In this case, I'm going to pull out a binomial term. Notice I can factor out of this expression an x minus 2. What's left?
Negative x plus 2.
I'll hold it. X squared minus 1. Now,
Okay.
there's a 1 in front of that.
Right.
Okay. So all I've done is divide both terms by x minus 2. Okay. Now, what's that called? Difference of...
difference of squares?
Correct. Now, that's one that a lot of people don't recognize because they don't think of 1 as being a perfect square number. But it is. So how does that factor?
X plus 1, x minus 1?
Now we have our zeros. What are our 3 zeros for this sum?
2, -1, and 1.
Now, if I want to graph it, I go to 2, 1, -1. Now, there's either 2 ways that this graph looks. It either looks like this, or, let me draw in blue, it looks like this, because it's going to have at most 2 humps, 2 local extrema, so it's going to be one of those 2 curves. How can I tell which curve it is?
The sign of the first term?
Correct. It's positive. In other words, this is what determines the end behavior. When x goes to positive infinity, what does f of x go to?
The same thing?
Correct. So therefore, I know this has to be the right model, not the blue line.
Okay.
So there's your graph. And when x goes to negative infinity, y goes to negative infinity, or f of x. I want to label this f of x. And that's the way cubics tend to look. In other words, the simplest cubic doesn't have any humps in it at all. The simplest cubic is this one, which is y equals x cubed. But the moment you add an x squared or an x or a constant, it puts a couple humps in. And that's a typical way that a cubic function will look.
Okay.
All right. What else?
We also had to label the y-intercept.
Okay. What's the y-intercept based on that function?
2.
Correct. In other words, the y-intercept is where x equals 0. The x-intercept is where y equals 0. That's a good thing to remember.
Okay.
So this point right here is 2.
Okay.
And that really is the only points of interest on that curve that I care about.
Right.
In other words, I've got 3 x-intercepts. I've got the y-intercept. There's nothing else of interest there. You know, it goes off to negative infinity that way, and it goes off to positive infinity that way. So there's really no other interesting points on the curve.
Right. Okay, we had one of them that was write 73 as a difference of 2 perfect squares if possible.
Okay, what's the general formula for a squared minus b squared?
A plus b, a minus b.
I'm glad you have it memorized. I would prefer you memorize it a minus b times a plus b. And I'm going to briefly tell you why. Because the next thing you're going to learn is difference of cubes. You're going to have to memorize that. Have you had difference of cubes yet?
No.
And sum of cubes. And notice there's something very interesting about all three of these. The first term has the same sign as what you're doing.
Okay.
The second term has the opposite sign.
Right.
So that's the reason I like people to memorize difference of perfect squares as a minus b times a plus b. Even though it's the same thing, you didn't say anything wrong by putting the plus first. You know, the associative property holds. But it makes it easier to memorize all three if you have a pattern.
Right.
Pattern is that the first term of all three is a linear term, and the sign is the same as what you started with. And the second term, the sign is opposite in the middle of what you started with. That makes it very easy to memorize. Okay?
Okay.
So, we won't worry about the cubes at the moment. And that's equal to 73. This is an interesting problem. I've never seen this kind of a problem.
Yeah, we did them a lot this year.
Really? This specifically?
Yeah, just like...
You're taking honors algebra too?
Yes.
Okay, let me think about this for a moment. What is going to equal to 73? Well, first of all, 73 is time, I believe. So I don't see any two numbers multiplying to 73.
Right.
Except 73 and 1. How about if I had 37 minus 36 times 37 plus 36? That's equal to 73.
Was that... So that's the solution?
Uh-huh. Well, what was the problem? What is A and B?
I was just right. 73 is a difference of two perfect squares.
Well, two perfect squares. The problem specifically said that?
Yeah.
Because these aren't perfect squares. In other words, this is the answer to that. 73 is going to be equal to 37 squared minus 36 squared. That's got to be the answer.
Yeah, I think it is.
Yeah.
I wrote not possible, and I got it wrong.
Yeah. No, it's a straight. I guess 37 squared is a perfect square. Okay. 37 is not a perfect square, but 37
I think
squared.
that's what. Yeah, I think that's what he meant.
So, yeah, it must be what it has. That's kind of an interesting problem, actually. Yeah.
So how'd you get 36 and 37?
I first of all realized that there were no two numbers that multiply to 73 other than 1 times 73. So one of these has to be the number 1, and the other has to be the number 73. Well, only 37 and 36 satisfy that requirement.
Okay.
And I guess technically, I would have to solve a couple of equations. In other words, I got a minus b equals 1, and a plus b has to equal 73. Add both equations, I get 2a equals 74, a equals 37. B must be equal to 1.
Okay.
So the key of this problem, actually there's a lot of keys. This would be an excellent problem. This would be an excellent problem for the SAT subject. But the key is knowing that the difference of perfect squares factors into a minus b times a plus b. Once you get this far and you know that that has to be equal to 73, well, now you're looking for two factors of 73, right?
Right.
Well, because 73 is prime, the only two numbers have to be, they made the problem easier by giving you a prime number, because now we don't have any choice. One of these has to be 73, the other one has to be 1. And that gives me my conclusion pretty quick. A has to be 37, B has to be 36. I like that problem still. It's a good one.
Okay, then the one after that was show how you know that 2 to the 50th minus 1 is a composite number by finding at least one factor.
Okay, composite means not prime.
Right.
What is that called?
Difference of two squares?
Yes. And it's important. I'm glad you said difference of two squares as opposed to difference of perfect squares. Even though they teach it as the difference of perfect squares, it actually works for any two numbers. If I had x minus 7, that's going to factor into the square root of x minus the square root of 7 times the square root of x plus the square root of 7. In other words, these don't have to be perfect squares in order to factor them.
We talked about this last time.
Okay, so the fact that you call that difference of squares is good. Now, what does that factor into? If we're looking at the difference of squares, in other words, we're looking at something that is a squared minus b squared. What's a?
2?
No, it's the square root of that. What's the square root of that? 2 to the 25th. Notice that 2 to the 25th times 2 to the 25th is 2 to the 50th.
Okay.
Minus 1 times 2 to the 25th plus 1. Now, They said, show that it is a composite number. Well, this shows it. Neither one of those is the number 1. So clearly, this expression is the product of two numbers, neither of which is 1, meaning it's a composite number. If it was prime, one of these numbers would have to be 1.
Okay.
Okay? So, obviously, that's not 1, and that's not 1. So, we have the product of two numbers being equal to this number, whatever that number is. It's definitely not prime.
Okay.
I like these problems. You're giving me problems I haven't seen. What school do you go to, Chris?
I go to Arapahoe.
Yeah, I've had other students from Arapahoe that give me extra tough problems. I have no idea they have such a tough curriculum.
Yeah.
Now that's not, you don't have an IB program there, do you?
No.
Okay. That's a good thing, actually. I hate the IB program.
Oh, really?
Yep, I do. I do not like the way they teach math. I get a couple of IB students every year, and they just make it as confusing as they possibly can.
Oh.
Like that's a good thing. I happen to think that's a bad thing, but... All right, so what else? In other words, these problems you're giving me are interesting, but they're not confusing. They don't confuse the issue.
Right. See, I think there are only 2 more that I had trouble with.
Okay.
Find the quotient of the expression x to the third plus 2x squared plus 8x plus 1 over x plus 5.
Okay. Notice, first of all, I have no way of factoring that cubic. The ratio of the coefficients is 1 to 2, 8 to 1. So I cannot group that.
Right.
Okay. It may be that this is one of the linear factors of that. Well, how can we tell? Let's divide it. Have you been taught synthetic division? Sure you have.
You showed me last time, and I think I remember most of it.
Have you been taught long division for polynomials?
Yes.
Well, let's do long division. It's not fundamentally any different. In other words, with synthetic division, I would make it a -5, and I would be doing adding the whole way. But with long division, I'm going to be doing the normal subtracting. So what's the first step?
X plus 5 into x to the third plus 2x.
First step is to divide that into that. That's the only thing you care about. You don't care about plus 5 yet. You don't care about anything else. That's x squared. Now I'm going to multiply the x squared by both terms, just like normal division. I must have left a square off of that. Yeah. Okay. Now we're subtracting. What do you get?
Minus 3x.
Minus 3x squared. Yeah, that's my fault. I left the x squared off there. Now I bring down the 8x, just like we would with long division, and start the whole process over again. In other words, divide that into that.
Negative 3x.
Now multiply that in both terms.
Negative 15x.
Now subtract.
23x.
Bring down the 1. Do the whole thing again.
23. And
subtract again. That's your remainder. Now,
okay.
The fact that that's not 0 means that x plus 5 is not a factor of this polynomial. There is something called the zero remainder theorem that says if you have a factor of a polynomial and you divide it, your remainder must be 0. If it is not 0, then it's not a factor. So what is the answer? It's this quadratic plus a minus 114 divided by the divisor x plus 5. So there is your answer.
Okay.
That minus 114 over x plus 5. Now, I could do the same thing with synthetic division. And when I would get the same answer. It's just faster. Notice that with synthetic division, you eliminate the variable. We don't really need the variable in. The only thing we care about is the coefficient. And that's what synthetic division does, is it eliminates the need for the coefficients and it turns subtraction into addition, which is a nice thing. Makes it easier. And there's nothing else about this problem that I can imagine we could do. In other words, if x plus 5 is not a factor of that, then when I do that division, I'm going to have a remainder, and there's not really much of interest.
Right.
And certainly this does not factor. But I'm not sure I would factor that anyway, even if it did, because I have a remainder. I honestly expected when you gave me this problem that x plus 5 would be a factor of that. Although actually I could have told that it was not. Because there's something called the rational factor theorem. So you haven't had that, have you?
No.
Okay. All right. So honors algebra 2 doesn't quite get to pre-calc, but close.
Right.
Because once you get into pre-calc, you will learn more about how to factor cubics and quartics. And it's very, very complicated and very, very difficult. So much more difficult than quadratics.
Yeah.
All right, what else do you got?
So the last one on here.
Okay.
This is also finding the quotient.
Okay.
It's x to the 4th plus 4x cubed plus 3x squared plus 4x plus 2 over x squared plus 1. Or actually, no, that wasn't it.
Oh, good. Actually, I know how to do this.
Actually, no, it wasn't a quotient problem. I'm sorry.
Okay. What was it?
Was a completely different one. It's write the expression 2x minus 3 or the quantity of 2x minus 3 times 3x plus 5 minus the quantity of x plus 1 times the quantity of 2x squared minus 6x plus 3.
And we're to simplify this?
It says write it in standard form.
Okay. All right, well, we're going to end up with a cubic, right?
Right.
Because we're going to have that times that. That's a cubic. So our final polynomial is going to be a cubic. So
right.
I don't really want to factor that. That's not going to help. Ooh. Unless the factor was 2x minus 3. Does that factor into 2x minus 3 times x minus 1? No. Good. Didn't want it to. So the best way to proceed here is just let's start creating the terms of our polynomial. Okay, multiply those two together.
6x squared plus 10x minus 9x minus 15.
Now, I don't need parentheses around that, but I'm going to put them just for clarification. What I do need is parentheses around this one, because of this minus sign right there. If it was a plus, I wouldn't care. But when it's a minus, that minus sign is going to apply to every term that is created when I multiply this times that. Okay? So let's multiply that times that. What do we get?
2x cubed minus 6x squared plus 3x plus 2x squared minus 6x plus 3.
Okay, now the only thing we have to do is remove the second. I can remove the first set of parentheses because it was only for clarification to begin with. To remove the second set of parentheses, I just have to change the sign of every term.
Okay.
So the sign of that will become negative. The sign of that will become positive. That will become negative, negative, positive, negative. Now I can remove the parentheses. Notice I have the minus 2x. Okay? Now we just have to combine everything. How many x cubed do we have?
Just one.
Minus 2x cubed. Let's draw a line through that. How many x squareds do we have?
3.
Now we have 6 there, plus another 6, that's 12, minus 2, we have a net 10. Let's draw a line through that, and through that, and through that. How many x's do we have?
4.
So minus 19 minus 22 plus 6 is minus 16. I believe. I hope I'm not making a mistake here with the math. What is our net number?
Minus 18.
There is our answer, I believe. Is that all they wanted was the final answer?
Yes.
Okay. Well, that's what you get when you multiply that and subtract that.
I think I just forgot to change the signs.
Meaning?
On the, you know how when we distributed the negative?
When I put parentheses around it.
Yeah, I did something like that.
You did it on the test. You didn't change the signs of everything inside the parentheses.
Right.
You have to distribute that negative sign to everything that's being subtracted.
Right.
In other words, if I have x minus y squared minus 2, to remove those parentheses, it becomes x minus y squared plus 2. I have to distribute that to both of these terms. That's why it's so important to put the parentheses there. Because notice that when we start this problem, we really don't have that in parentheses. I mean, we have the product of two things. But after we multiply x plus 1 times this trinomial, we have to put the result in parentheses. Because that product is what is being subtracted.
Okay.
And that's a good lesson. There's a lot of algebra problems that have that. You have to add the parentheses where there weren't any to really begin with. And where you have to think about that is where you're subtracting stuff. Like I said, had that been a plus sign, I would not have needed to worry about the parentheses. Because now I don't have to change the sign on anything that's inside of there, so I wouldn't need the parentheses. But when it's a minus sign, always remember you need to subtract.
Okay.
It's kind of like this. Let me think for a second. Okay, if I did that problem there. Well, what's the common denominator? X times x minus 1. This phrase here is x minus 1 minus, I gave a bad problem. I meant to make this the x, and this to make the x minus 1. So if I had this problem, this is going to be x there. This is going to be x minus 1 up there over the common denominator. But notice that if I don't add the parentheses, I'm not getting the right answer. I have to put parentheses there. I have to add them. They were never there to begin with. But I have to add them because this minus 1 is going to turn into a plus 1.
Okay.
Okay? So it's a similar problem. Very similar in that sometimes you have expressions like that. You have to make sure you put in the parentheses around the answer of that product. Because of that minus.
Right.
All right. Is that it?
That was pretty much it for this test.
Okay. Well, let's see. We have another session scheduled on Thursday. Is that right?
Yes.
Just verify the time at the same time, I believe, right? 2 o'clock?
I think so.
Yeah. Okay, on Thursday, Chris, I will merely text you the meeting ID number. I won't call you. I will just text you.
Okay.
And you should have an icon on your desktop that looks like this. Looks like a flower.
Yeah.
Should say go to meeting, or does yours say join go to meeting or go to meeting?
Hold on.
Never known for sure.
I think it just says go to meeting.
Okay. I figured it probably said the same thing, and it's probably this orange flower also. But
yeah.
In other words, next time you don't need to go to the site, join go to meeting. Just need to double click that icon and put in the meeting ID number. And
okay, which number do you have?
For your phone number, or to text it to you, I have 290-0707.
There might be a better one to text it to.
Okay, let me have that one, and I'll change it.
720-469-6718.
That's your phone number?
Yeah.
It's your cell?
Yeah.
That's what I'll use from now on. I'll go ahead and change my phone contact for that.
Okay.
Okay? Chris, I will talk to you on Tuesday. Oh,
all right, thank you.
Is this email address the right one? Grobber60?
Yeah, that one should be fine.
I will send you a link either later this evening or in the morning that will show you how to find the recording of this session.
Okay.
It takes my computer a few hours to process it, but
yeah.
If you want to, you will have a chance to review this.
Okay, thank you.
Okay. All right, and to exit out of this, just click on the X in the upper right hand of the control panel.
Okay.
All right, Chris, talk to you in a couple days.
All right, thank you.